Thanks, Donna, and thanks to all our sponsors. And it's lovely to be here on this cold and rainy night to talk to you about what I think is one of the more interesting, if not the most interesting, emerging exploration stories in Western Australia. And I hope by the end of this talk, you'll have some understanding of what we're unveiling here. That's why it's unveiling a new province, a new global scale province, and that's important. It's probably one of the most significant new carbonatite provinces that's been found for multiple decades. And in the world that we're in, the world of geopolitical uncertainty and a strong focus on some of these commodities, it's actually very important for this country to have those sort of resources. It's the way that we'll probably, continue to sort of survive and prosper in the 21st century. So, disclaimer and then acknowledgements. Now, while I'm the person standing up here presenting this, you'll appreciate that the work that I'm showing you is the product of a lot of hard work, both in the field and in the office, from a very large and dedicated Encounter team. So I want to acknowledge those, including my co-author, Sarah. Secondly, I might just get some water here. A shout out to our service providers as well, because in our sector, as a junior mining company, you don't do everything yourself. You need your service providers. You need good relationships with them. They're critical. So I want to acknowledge those and our research partners, and we'll talk a little bit more about them later. Then pretty much no greenfields exploration, successful greenfields exploration occurs in this country that's not fundamentally founded on the fantastic pre-competitive geoscience data sets that our government surveys provide, and this is no exception. At the federal level, Geoscience Australia; at the state level, the Geological Society of Western Australia. And for those of us who work globally, I'm sure we have a real appreciation of the value of these data sets compared to what we might have in other jurisdictions. And lastly, the traditional owners of the areas covered by our project, the Pana Ngurapa and the Jammu Jammu, and we acknowledge their support for this ongoing work. So what am I talking about here? I'm talking about, a project that's located in probably just about the most remote part of Australia. So it's on the north shore of Lake Mackay, which is a rather large dry salt lake in the middle of Australia, right on the West Australian NT border. Why do I say that it's the most remote part of Australia? Well, I think I can credibly say that because this is the area where the very, very last traditional people came out of the desert, the famous Chindabi 9, and this was in the early 1980s. So that, I think, talks to the remoteness. But having said that, this is going to be a sealed road, this is a port, and it's something that will not be very difficult to develop compared to many other sites. So there's remoteness and there's remoteness. Why we think this is the next great mineral province? I think one of the reasons is that when a new province is discovered, what is often characteristic is multiple rapid discoveries following quickly, one after another. And that is in fact been the situation here. And we've had a very high conversion rate of conceptual targeting to economic discovery. These resources are globally significant, and the processing pathways, the capital investment is not particularly massive. So we can see very, very quickly getting through to production on something like this. But carbonatites are treasure troves. They come straight from the mantle. They're treasure troves of metal. So niobium is our focus. It's a very high value product, but we're also seeing very high rare earths. And if those of you who saw our announcement, I think it was yesterday, the day before, not only are we starting to see very high levels of rare earths, carbonatites are most known for being dominantly light rare earths, and the critical heavies, the dysprosium and the terbium, are normally not well represented. We are starting to see those high levels, so that's a little bit different, and that's a bit exciting. But as I'll explain to you a bit later, we fundamentally went out there because we were chasing gold and copper. We were chasing IOCG styles of mineralisation, and there's an argument that IOCGs and carbonatites are on a spectrum. of mantle-derived alkalic magma, and there's a few other things in that spectrum. And we are seeing those sort of sniffs as well. So we're still very much focused on those sort of opportunities. So we genuinely believe that the most important discoveries in this region are potentially still ahead of us. Just to give you an overview, in brown are where we've defined these carbonatite complexes. These are basically dike complexes, and you can probably see, I think even if you weren't a geologist, you could probably see that there's a very obvious and strong relationship with these fundamental structures that we image in the magnetic data. We also image in the gravity data. And if over time we get some more fundamental, deep-looking data sets such as magnetotellurics, I'm fairly confident that we'll show that these are major translitospheric structures. I mean, no surprise, carbonatite magmas come from the mantle, that's what we expect, but it's actually quite dramatic how effective these data sets are in our targeting. And of course, areas of complexity along these things are a focus. While I've got this diagram up though, I will point out the areas where we have defined and reported resources at Crean, Emily, Green, and that's WA1's Looney deposit there between our Emily and Green deposits. And I'll also point out though that we're continuing to find more mineralisation. So in July, we announced very significant intersection end of hole here at Joyce. So we're following that trend. And we're quite excited about these trends. About a year ago, the GSWA reported some heavy mineral sampling and the fact that they were finding detrital cuprite in a location about there. And that fascinates us because that was already one of our conceptual targets. So we'll be out there pretty soon as well. And we did drill a vein of chalcopyrite out in here. So I think that talks to the overall potential. So just to summarise our timeline, when we look at our main deposits, our discovery intersections were in July 24, and by May 25, we had released our very first inferred mineral resource estimate. And now we're continuing to drill to extend and grow these things, but we're also still looking to find new deposits. And I mentioned Joyce, 9 metres at 2.2% niobium oxide to the end of hole. We have a very, very active program out there at the moment. This year we'll be doing plus 40,000 metres of diamond, RC and air core. Air core is an extremely effective exploration technique out here. People talk about remoteness, but remoteness has 3 dimensions as well as 2 dimensions. So if you're somewhere where you can drill rapidly through 10, 15, 20 metres of cover and test the bedrock, it's in a remote area, but compare that to drilling under 300, 400, 500 metres of cover in somewhere like the Stewart Shelf, right? And I think you can start to see that we have these different dimensions of remoteness. And we are very much in the process of our metallurgical test work. Once again, acknowledging the government, EIS co-funded diamond drilling has been an important part of our process, and we're continuing to do that. So we're very grateful for that support. So just as introduction and just a quick outline of what I want to talk about. I want to give you a little bit of background on niobium because I'm not sure everyone has a detailed understanding of this metal and what it can do for global society. I want to talk a little bit about background geology on carbonatites because I think that's important context. I want to talk about our discovery story and you can just get an idea of how that sort of rolled out for us. And then a little bit about the rocks that we see, including some rock pictures. My colleague Peter Buick criticised me for not organising to bring any rock samples here, which we should have done because they actually are really quite cool, these carbonatite rocks, but okay, next time. And then a little bit on deposit scale controls on mineralisation, and then finally with what's next, because as I've said, we believe this is just the start. So niobium, first of all, it's a high value commodity, the pricing is stable, and it's sort of basically an oligopoly where there's 3 producers, 2 in Brazil, the Araxá complex, CBMNM, and CIMOC out of the Catalan 2 complex, and then there's a sort of a hard rock, sort of lower grade deposit called Niobium in Canada. The processing is not difficult. It's not like rare earths. It's pretty much conventional flotation to get a concentrate, and I'll talk a little bit more about that. But it is a critical metal. It's used in defence, nuclear, steel, and battery applications, and a very strong global demand. And you can see the price. We're talking about $40 to $50 a kilo for, $1,000 a tonne for niobium oxide. So compare that, for example, to copper, where we're around about 8 or 10,000. So the value chain, we start off with our niobium ore, we mine it, we concentrate it, basically crush, grind, flotation, and then we can produce a couple of different products, ferroniobium, and there's a smelting process to do that, or niobium oxide, and those are kind of different routes in terms of going to market. And then finally, niobium alloys, which is sort of way downstream. But obviously, like you would have seen with lithium and these other commodities, you're kind of going up the value chain as you go in that direction. So the two main end products, ferroniobium, and at the moment that's 88%. And I suppose the basic thing that ferroniobium does is it makes steel lighter. Like if you're building something like the Burj Khalifa or 1,000-metre high skyscraper, it's very important that your steel is light for the same strength. And of course, in just about any application that uses steel, which is most of everything we use in our modern society, if you make it lighter, you make it more energy efficient, whether that's in a car or in any sort of plant. So we see this continuing to grow, and very much so in the context of the decarbonisation agenda. But then there's another interesting thing that we're seeing, which is niobium oxide, and this is kind of a latent market, but it's used in a number of highly specialised applications, such as superconductive magnets and so on. But I think the thing that really interests us is groups are now looking at adding niobium to lithium batteries, because it does something pretty cool, and that is it stops them bursting into flames, which tends to be a little bit of an issue with these batteries. So, and I think, and some of my colleagues can probably answer this better than me, but I think we've now got some of the battery makers starting to produce a battery product with niobium oxide. So that's why we're interested in niobium. So let's talk a little bit about the geology of the host rock, or the host rock complex, because it's really a bit more than a simple host rock, which I hope to explain to you. So carbonatites, and I apologise for the introductory level of this, but just to provide a context for everyone. What is a carbonatite? It's a rare rock type. It's an igneous rock that's actually mostly composed of carbonate, and as we all know, that's uncommon. Why? Because it's come from the partial melting and various processes on the way of CO2 metasomatized mantle. But we care about carbonatites because they're important economic hosts for rare earth elements, niobium and phosphate, and in fact pretty much all the world's economic niobium does come from these deposits, but the majority of the rare earths as well. And in at least one case, and that's Palabora in South Africa, they also host significant copper deposits, and that's quite interesting to us. And for those people who are into the sort of whole IOCG thing, you kind of think of, well, is that a spectrum? I think it probably is. They're typically associated with alkalic igneous rocks in incipient rift systems, implying formation through low-degree mantle partial melting, and probably in response to some broad, long wavelength mantle upwelling, like we see in the East African rift system at the moment. What they do have, and I've already sort of more or less shown you that, but they have a very strong association with these major translithospheric structures. And I think that's very clear and very predictive. Now, these deposits are subject to supergene enrichment. Well, I guess when you're dealing with carbonate, it's something that sort of leaches pretty well, and you can enrich something. So most carbonatite deposits, both the ones that produce rare earths, such as Bonobo and Mount Weld, and the ones that produce niobium, have zones of supergene enrichment. That's sort of the case at the moment, but hypergene grades can actually be quite significant. So we can see hypergene grades greater than 1% niobium. And some aspects of the mineralogy of the hypergene is actually as good, if not better, than the supergene from a processing point of view. And the Niobium deposit in Canada is an example. That's sort of a hard rock hypergene deposit. So before I go a little bit further, I just want to share with you some key geological terms that we need to have if we're going to think about carbonatite. So first of all, pyrochlore. So what's that? That's the main niobium hosting mineral. So I don't need to worry about its formula too much, but that's the main mineral we want to see. And importantly, it's a dense mineral. So, that helps us on the processing side. We also see, there should be a B in there, columbite, another niobium hosting mineral. Apologise for that typo. And then another mineral that word that gets thrown around is crandallite, which is really the weathered product of apatite, because these systems have quite a lot of apatite in the primary in the weathered zone. But the terms that are significant for understanding the genesis and understanding the controls on mineralisation are the next two. So phenite. What do we mean by phenite? This is a metasomatic wall rock alteration, and these things typically look sort of reddish. They're alkali metasomatism, but they're typically dominated by alkali feldspar, so kind of hematite and not that different to what you might see in a IOCG context, though they do also have quite interestingly these sodic amphiboles, things like riebeckite and glaucophane, that like you might think you're in like a blue schist, but you're not. It's just in the phenite. So this is the halo that we see, because these carbonatite magmas are full of juice. So when we emplace them, they react with the wall rock, and they produce phenite. There's another rock though, and this is going to be really quite important in the niobium story, that we call glimmerite. So what's glimmerite? A glimmerite is a rock composed almost entirely of a dark mica. It might be biotite, it might be phlogopite, somewhere on that iron to magnesium spectrum. Why is it called glimmerite? Because it probably glimmers when the sun shines on it, I'm guessing. But the glimmerite zones, we see significant accessory phases, including sulfides. Pyrite is common. We do see the occasional sniff of chalcopyrite in these glimmerite zones, which is what interests us. But that's a critical rock type. And then the other rock type we see is called phosgorite. And a phosgorite is really magnetite, apatite. So it's kind of probably produced by some sort of fluid immiscibility from the carbonate. And then it will typically have a silicate with it. And that silicate can either be usually an olivine or a diopside, sometimes a phlogopite as well. So Anthony William Jones has produced a model which I think is quite robust, and he's validated this model with experimental petrology for the formation of pyrochlore. Because the thing about pyrochlore, it's our main mineral, but it's extremely soluble in carbonatite magmas. So it's very hard to concentrate the pyrochlore simply by typical igneous fractionation processes. But what Williams-Jones has shown us is that if we imagine the sort of progressive emplacement of one of these zones of intense carbonatite magma and related metasomatism, and it's obviously going to be in a complex sort of fracture environment, we can see a sequence where we initially form these volumes of phenite alteration, and I will show you some pictures a little bit later on what these things look like. And then once the phenite is formed and the later carbonatite magma comes through, it tends to react with the phenite to form the glimmerite. So the glimmerite is kind of like the alteration. And what Williams-Jones and his co-workers have shown is it's that alteration to produce glimmerite that actually precipitates the pyrochlore. So, simplistically, you've got the pattern phenite, glimmerite, and in detail, of course, the glimmerite is going to have lots of veins of carbonatite and things in it. So it's going to be fractal. And then the pyrochlore as a response to that sort of interaction. So, we believe that's the key process. And for those that are interested, I refer you to his papers. The other thing that's quite important to understand about carbonatites is like any volatile rich magma coming up from the mantle, its emplacement geometry is going to be a function of confining pressure. So these things are going to start off as dikes. As they come closer to the surface, they're going to be pipes. And then finally, they're going to become craters. And this is the diamond guys. I see a few diamond guys there smiling, Grant. But the diamond guys know this pretty well. And they talk about, you know, crater facies and dike facies and diatreme facies. But, you know, from a physical mechanical point of view, a carbonatite and a kimberlite are basically equivalent. They're both extremely fluid charged magmas. So what that means is that if you erode one through about here, it's going to look like some sort of plug, and it's going to have a lot of concentric rings, you know, ring faults and, you know, ring diking and so on. If you erode them down about here, they're going to be more like dike complexes. Now, why that interests us is if you think about the Williams-Jones model, where you're fundamentally depositing the pyrochlore as a function of reacting with the wall rock, a multiple dike scenario gives you way more opportunity to do that than a big plug. So it's quite interesting conceptually in terms of what you want to see. Now, if we go to Arashar, which is kind of the big giant of carbonatites, it sort of, you know, dominates production, dominates global reserves. It is a typical concentric complex, but the mineralisation isn't. So when we look at the actual niobium mineralisation, it's a later phase that's superimposed, sort of like that's a cross section through there. It's kind of like a vertical dike complex. And in the context of the model that I was just speaking to you about, you've got the carbonatite as a discrete dike, and you've got the glimmerite zone and the mineralized and the phosphorite. So it's this glimmerite phosphorite that seems to be quite important in hosting the mineralization. Some other examples, Catalão, which is the second big Brazilian producer. Most of the mineralization, the niobium mineralization, is coming from these dike complexes. So if we look at the example of Morro de Padre, cross section through it, and you can see it's basically a series of these dikes and phosphorites and you know, I mean, phlogopite phosphorite's probably what we would call glimmerite. And of course, we all know about Bayonobo, probably the most famous carbonatite complex in the world, because it's the fundamental basis for China's dominance of global rare earth industry. And Bayonobo looks nothing like a plug. It obviously looks like a dike, and it's of course best known for its rare earths, but it does host significant niobium, not exactly in the same spot. These iron ore bodies in the Chinese literature are basically our phosphorites, our magnetite apatite. But when we focus in on here, where we see the niobium, I think it's quite interesting that the niobium occurs in this zone of albertization and biotization. So, you know, you're somewhat interpreting the Chinese literature. They'll never let any foreigner go there these days. But I would interpret that as a zone of glimmerite and phenite alteration. And we're also typically seeing the niobium on the margins of the system as well. All right, so that's just in the time I have available, and I think I'm going okay. That's our geological context. So what's the discovery story here? Well, we first targeted this area for IOCG copper gold, and Terry Hronsky had brought to our attention this very prominent anomaly, and it was what? Right. Keep going. All right. And in a very remote area, it was extremely remote in 2019, but we had a crack at it, and we pegged the ground, and then we went out there, and at that stage actually in a joint venture with Newcrest, and we drilled the first hole into that anomaly. And we weren't able to complete the hole for various technical reasons in a very difficult operating environment. However, we realized when we drilled that hole, when we got the assays back, we had something that was highly anomalous in niobium, rare earths, copper and gold. So we were seeing that IOCG sweep. It's the same sort of stuff you see around Olympic Dam. Once again, that's the fingerprint of IOCGs versus carbonatites and why we think they're a spectrum. But so then we thought about how to follow that up next. We're looking at the other anomalies, but then along came WA1 and they made a couple of discoveries that happened to be just right on our boundary. And on the basis of those discoveries and the work we were doing, we started to realise the fundamental architectural control was driving things here. So very rapidly, we went out there with the Air Corps rig and we started to discover these complexes and you know, in detail, a lot of really good work in tough field conditions, understanding the regolith. I'll show you something on that in a minute, understanding the controls. And, you know, so now we, you know, 2025, early in the season, we released our MREs and now we're following this. But just to put you on context, so that's, I showed you Bonobo before. That's Bonobo at the same scale, the Bonobo dike complex. So we really are, this is why I'm talking about this as a world-class discovery, a new world-class province discovery. I mean, that's considered the greatest carbonatite in the world, and our systems are showing that sort of strike length, that sort of scale, and we really haven't found the end of them yet. So why did we go there? Well, Encounter is a company that was founded to do greenfields exploration. That's in our DNA. We're about making those world-class discoveries that really matter both to our shareholders and to the country for that matter. And we know one important thing, and that is the really, really big discoveries are where you go and look in a new search space, where you look where people haven't thought to do it before. So we recognise that. We recognise the West Arunta region. We didn't understand the geology very well. I mean, it's still relatively mysterious, but we knew here was this big area of prospective looking geology. We could see it in the magnetics that really wasn't very deeply covered, right? I mean, that's the exciting thing. I talk about remoteness, but if you can find something that's, you know, in places only a few meters of cover, that's exciting. Why? Because you can explore rapidly and cheaply. Okay, so, and we recognise that it was in that sort of Proterozoic time period where so many of our big deposits are. We were focused on IOCGs originally, and I think so were probably WA1 when they went out there. But I continue to make the point that we shouldn't think about these things as pigeonhole categories. We should think of them as spectrums of mantle-derived magmas coming up these big cracks. And speaking of big cracks, that was always a critical targeting element. These regional scale structures. I mean, regional scale structures are a critical targeting element for everything, but it was really kind of pretty obvious here, and it's proved pretty successful. The regional context is we were sitting here in the Arunta region, and that term covers a whole lot of geology really, but we're dealing with some really fundamental big structures. Basically an orogenic belt that develops on the southern margin of the North Australian Craton, which is one of the cratonic cores of the Australian continent. And this was in 2013. This is sort of the geology. This is a raw geolese work, and it's not very precise, and basically in detail probably not that correct, because most of this isn't Carrington Sweet. It's probably more like these Paleoproterozoic metasediments that have been identified as the Lander Rock Formation, which sits above the Tanami group, and that's probably broadly correct, though likely to be more complex than that. And then we did our work, and our work emphasised the structures, and we saw this endurance fault zone coming through. We saw some of these other structures, and we saw the sense that there was a whole lot of really important structures converging here, and there was the odd little sniff of copper. I think there was a 400 ppm copper sort of soil sample, and that really started to bring us in here. I mean, we understood that we had these extensive areas, the Morava Basin, the Amadeus Basin. These are all Neoproterozoic basins that are part of the bigger Centralian Basin. So we knew we were dealing with sort of Proterozoic inliers in there. We knew we had these extensive areas of granite, but very little exposure. It turned out that a lot of the exposure that the survey had mapped when they went out there was in fact outcropping Permian. So probably even less exposure than we thought about. And I guess one of the things that did interest us, and we subsequently validated with our own work, is there was some GSWA geochronology of this hole here that was probably the only hole drilled in this anywhere in this province before we went out there. That's to the south of our project area, and it identified a thermal event at about 1590. And of course, you all understand that we get excited when we see 1590 because that's the Olympic Dam event. So that was partly driving our thinking. I guess as we've collected more data, and this is from acknowledging the GSWA again and Dave Kelsey's work, but 2024, and we do have another big piece of geochronology coming out. It's still in publication, so we didn't really want to talk about it today, but within the next month or so it'll come out. And what this is showing us is, we've got the age, the sort of Carrington Sweet age, the sort of 1770, 1780 sort of granites, probably just immediately sort of post the sort of Tanami event. But then we see this thermal event here, which is the Hildeborough event. And, I'm still interested in that. But then it does look like the carbonatites are actually broadly coeval with and the carbonatites occur associated with other alkalic rocks such as lamprifiers and so on. And it looks like that they're broadly coeval with the initiation of the Centralian Basin and the Gardner Dyke swarm. So, but we might get two bites of the cherry here. So just to summarise the geology, our mineralisation is hosted by an alkalic magmatic complex and the adjacent strongly altered wall rocks. It's not just in the carbonatite, it's in these altered wall rock complexes. And, we're fairly confident that these are Neoproterozoic in age. Having said that, these are big cracks, and big cracks get the juice more than once in their history usually. So who knows what we'll see as we continue to understand this a bit more. At the regional scale, this complex is strongly spatially associated with a suite of major structures that, oftentimes we try and apply this translithosphoretic targeting concept, looking at cryptic structures, and people can be a bit sceptical. This is not one of those times. This is one of the times where just about any data set is going to show you those structures very clearly. In detail, the phenite altered wall rocks, they host veining related to the carbonatite, so it's kind of more of a fractal thing, and that veining, it's probably a bit of a moot point. Is it an igneous carbonatite vein, or is it a hydrothermal fluid that's derived from that carbonatite? Probably doesn't really matter. And what this alkalic complex is intruding is a sequence of high metamorphic grade, probably sort of mid-amphibolite and up wall rocks. Now they're dominantly paragneiss and felsic orthogneiss, but we do see intercalations of BIF, and the BIF gets overprinted by the carbonatite to generate a lot of sort of massive magnetite alteration, and that turned out to be what our initial hole was actually drilled on, and metamorphic rocks. And so probably what this Paleoprote host sequence is an original pericontinental rift sequence that formed on the margin of the North Australian craton in the Paleoproterozoic, and there was, inverted into an origin in the, at more or less at the end of the Paleoproterozoic, and then was, deformed and intruded at that point, and then sat there and then was overprinted by an extensional event at about 800 with the initiation of the Centralian Basin. And I'll finish with saying that this gallop through the geology, the belt is extremely poorly exposed, but mostly only by a thin veneer of Cenozoic sediments. And that's what makes it so exciting from an exploration point of view. But there are local areas of thicker Permian cover that we're, as we explore, we try and understand. Okay. So once again, just to highlight the regional control, and in case people were wondering, the sort of naming convention here is to do with Shackleton's expedition, the famous Shackleton expedition to Antarctica that started in 1914 and didn't end up so well. But they did all get back. Elephant Island fault. The Elephant Island was a place where they sought refuge, the group that didn't get in a little boat and go to South Georgia. And it's a very small and grim place, unlike this fault, which is very big. So you can see the very clear association. Actually, one of the interesting things about the Elephant Island Fault is that it's actually a neotectonic feature as well. If you look at the current digital elevation model, you can quite clearly see it. So there's some sort of modern reactivation. Maybe it's even active today. There's quite a bit of neotectonics in Central Australia. Stromness Fault, that was the whaling station that Shackleton finally staggered up to the door of when he got there to South Georgia. Okay, and you can see our deposits, Emily, Green, and Cream. But you can also see that our mineralisation, and we're currently quite focused in this area, continues, and we're focused in this area in extending these systems. So what do the rocks look like? I'll start with the alkalic igneous suite. So we have our carbonatites. They're basically kind of white rocks. They're quite cool. They can have lots of magnetite in it. Sometimes they can have sort of pyrite in it. When they're weathered, there's kind of ochre-like stuff. But we also see them flanked by these ultramafic lamprifiers and mafic lamprifiers. So there's some examples intruding the gneiss. There's a lamprifier intruding the felsic orthogneiss, probably with a little bit of phenotization. And then we see this sort of glimmerite. So this is this black stuff here. This is the carbonatite intermingled with glimmerite, and that's probably the sort of thing that a lot of the proto-ore, or not even proto-ore, sometimes probably quite high-grade ore in the primary, that the supergene is developed over. A few more examples. These are dolomitic carbonatite. I'm not really sure there's much sort of significant visual difference between the two. A lot of people talk about dolomitic versus calciocarbonatites, like there's significant differences. We haven't yet really seen that. And this is the phenite. So these are examples of phenite. So basically red rock alteration. I mean, the sort of stuff you would see in the halo of an Olympic Dam or the halo of an Ernest Henry. If anyone's ever worked on those deposits, this sort of pervasive red, feldspar alteration. And then here's more about glimmerite. And remember what we said, that we think this process of creating the glimmerite, this wall rock alteration, is in fact the key process that drives pyrochlore deposition. And then our older rocks. These are our Paleoproterozoic sequence. We've got BIFs, we've got paragneiss, we've got metagabbro, paragneiss, felsic orthogneiss. Some of this stuff is probably what the survey would call the Carrington suite. Some of it, though, is this 1590 event, this Hildebert event. And over time, we'd like to sort of understand that a little bit better. Some more examples: amphibolite, mafic pegmatoid. Now, that mafic pegmatoid is often enriched in niobium and rare earths, so that might actually be something more akin to our syn mineral lamprifiers rather than the wall rock. Siltstone, metaconglomerate, schist, dolerite. We do see some quite late dolerites, probably the Gardner type age, and then felsic pegmatoids. All right, so at the deposit scale, what can I tell you about controls on mineralisation? Well, basically, it's associated with zones of supergene enrichment that are developed over these carbonatite dikes and related wall rocks. And if anyone's ever worked in supergene enriched deposits such as nickel laterites and so on, you'll understand that while people will always draw these kind of layer cake profiles, in reality, any supergene profile is way more complex than that and strongly governed by structure. So quite heterogeneous, and really what we see is no different. We wouldn't expect it to be. There is a general correlation between the thickness of the supergene weathering profile and the strength of the mineralisation in terms of grade thickness. And, if you think about the supergene process, just from a mass balance perspective, that's sort of what you would predict. Not always, but in general. We don't have that much data for the primary carbonatite, but there is certainly quite broad local host intervals of plus 1% niobium mineralisation. We have not included any of that in our inferred MRE because we're focused on most efficient sort of pathway to production, which is very much around the supergene. But we think there'll be, I mean, obviously Niobium produced from hypogene, and some of the Brazilians produce a bit from hypogene. So that's a massive upside in the future. We see a wide range of niobium grades within the host carbonatites, and although we do recognise both the calcio and dolomitic compositions, we yet to see any sort of systematic variation in mineralisation related to it. Now, rare earths come along with the niobium, and at any particular location, for example, the really quite impressive intersection that we released earlier this week, that was the highest grade rare earth intersection we'd seen. Will, you can remind me, but it was about 8%, I think, total rare earth, so quite good. And we typically see within the same part of the profile, the niobium and the rare earths at any particular location. But throughout the project area, we do see significant variations in rare earth niobium deposits. So we see the cream deposit in particular, which is the one along the northern structure, that's the highest rare earths of any of the deposits we see. Now that may be saying, given that we have these two main corridors, it may be saying that that northern corridor is fundamentally more enriched in rare earths, but it's still very, very early days. So as we'll continue to explore, we'll understand that a bit more. Now, some of our geologists in the field have suggested to me that dolomitic carbonate, which is more typically on the margin of the system, might host higher rare earths as well within the system, but that's something that we're really not very clear about, still very early days. I'll just quickly, to go down to a bit of detail at the deposit scale, I'll show you an example from Green, which is our largest deposit, where we've got at the sort of 1% cutoff, 12 million tonnes at 1.6% niobium, and we haven't really modelled or paid much attention to the rare earths and the phosphate here, which is concentrated on the niobium, but you can see the sort of basic geometry of the deposit and sort of reflecting this architecture of a dike complex. And when we look at a cross section through the deposit, you can see the sort of grades that we're getting, and you can see this sort of heterogeneity in the weathering profile. These are the sort of results that we're currently following up and extending. Oftentimes we've had holes that have sort of ended in mineralisation in the weathered zone, so we've had to come back and re-drill. The regolith profile, this is a picture of what a typical one looks like, where we don't have significant Permian on top. So, sand and gravel, not much, right? A bit of Aeolian sand. So this is what I mean when I talk about thin cover into a bit of a jury crust mottled zone. And then, the clay zone can be quite white. I mean, you are starting off with something that's pretty white, I guess. And then we have this palette. I mean, these are the zones that are really leached. And then we get the upper saprolite, and it's really sort of about, I mean, sometimes it's the palette zone, sometimes it's the upper saprolite, but this is where we start to get our grade normally, and then we ultimately end up in our fresh carbonatite. Permian, and we've actually confirmed that these are Permian sediments, as you would expect, sort of glacigene. They've got the faceted pebbles and all those stuff that you expect in glacial deposits, but we did do palynology to confirm this. Widespread throughout the project area and quite a lot more extensive. Like if you go to the sort of most recently published GSWA mapping, there's actually quite a bit more Permian. Sometimes in these channels it's up to 130 metres thick and typically sitting under the tertiary gravel and calcretes. Now, the relationship between Permian and mineralisation is quite interesting. In probably the majority of cases, if you see the Permian, it inhibits the development of a strong supergene profile, but we've got some cases where we see particularly strongly enriched mineralisation immediately below the Permian cover. What that might be telling you is, we often think of supergene processes just in one dimension as a vertical deflation, but of course in real life they're not. I mean, if anyone's worked on the martite, goethite, iron ore deposits in the Pilbara, you'll realise you can only understand those things in terms of a much more three-dimensional fluid flow system. So I suspect that's probably what we're seeing when we see enrichment under these Permian channels. We're probably dealing with three-dimensional pathways of supergene fluids along those corridors. All right, I used up my 45 minutes. So just to finish, what's next? Well, we believe that we've only just started to understand the full potential of this province. Our targeting model, which is really just quite simply based on following the key mega fault zones and then very low cost systematic testing of the targets along it, has been and continues to be highly successful. We support that though with a strategy of committing to collecting key geoscientific data sets at the regional scale. This is when you're opening up a new province, this is what you want. You want to understand the whole province. I mean, this province is over 100 kilometres long. That's, to put people into a goldfields analogy, that's like the southern end of the St Ives camp, somewhere like Junction, all the way up to Kalgoorlie, right? That's the scale that we're talking about here. So if we're going to be effectively targeting within that area, we need the data sets. So you saw the high resolution magnetics that we can see the structures in. I probably haven't put it in this presentation, but our gravity data, which we put online as well in our releases, shows the same sort of architecture. Broad coincidence, though of course when you see mismatches between gravity and magnetic data, that's always telling you interesting three-dimensional information, so that's important. And then the last data set that we've just collected, and I did beg Will to let me show it, but he wouldn't let me, is the airborne EM survey, because that's fascinating, right? It's amazing what that's showing. Okay, and we do remain mindful of the potential for copper mineralisation in the belt, and we do have some positive indications in some of the current data, some quite interesting sniffs, and you know, we feel like that could manifest as either a Palabora style carbonatite hosted mineralisation, or maybe something a bit more like IOCG. I mean, you know, we probably don't have any massive hematite type bodies. I think we have scanned for that, but I think there's an interesting spectrum there. So I showed you this diagram before, but just to remind you of the scale, that's that sort of 100 kilometre plus extent that we're looking at. And rare earths. So this is from the announcement that we put out earlier in the week, and that's the sort of Mount Weld pit shell. And this is not every diagram I showed you so far. When I've coloured the dots, that's been niobium. I'm now colouring the dots with rare earths. So the purple, that's greater than 2% total rare earths, and we can see we've got these very significant size corridors emerging, and particularly interesting up in here, and particularly interesting that we're seeing very anomalous levels of heavy rare earths. That's not characteristic of carbonatites. They're known for the neodymium and the praseodymium, but they're not known for the dysprosium and the terbium. So I don't know where that's going to take us, but we'll certainly be following that. And then finally, and I acknowledge Marco Fiorentini, I think he's in the audience. He's one of our key research providers here, but we have many of them. We want to learn what's going on here. If you get onto a major province discovery, I think it's incumbent on you to try and understand it, understand the geology. So yes, we can do air core drilling and we can find the supergene stuff and we can report it. But if we're going to see the full value of this province, we need to understand it. So we're really actively engaged in that research process. So we commissioned some geochronology, and unfortunately not quite out, so I haven't been able to release that, but that'll imminently come out. We've got a research PhD, Holly Cook at the University of Adelaide. We've got two honours projects on Hurley and Green, and then we've got a large ARC linkage project through Marco's group with UWA and ANU, and just sort of flagging some of those groups that we're working with in that effort to take our knowledge of this province forward to the next level. And thank you. I think that's it.